Our lesson today is on scatterplots and correlations. We'll look at explanatory and response variables, how to construct scatterplots, interpreting scatterplots, and measuring a linear association using correlation. We have two kinds of variables that we'll study. A response variable measures an outcome of a study. An explanatory variable may help explain or influence changes in a response variable. In many studies, the goal is to show changes in one or more explanatory variables actually cause changes in a response variable. However, other explanatory response relationships don't involve direct causation. An example of an explanatory variable is the amount of rain. The response variable would be weed growth. Another example of an explanatory variable, winning percentage of a basketball team. The response variable is attendance at games. Another example of an explanatory variable is the amount of daily exercise, and the response variable is resting pulse rate. We learned to use scatter plots in order to look at the relationship between two quantitative variables. A scatter plot shows the relationship between two quantitative variables measured on the same individuals. The values of one variable appear on the horizontal axis and the other variable appear on the vertical axis. Each individual in the data appears as a point on the graph. To make a scatter plot, decide which variable should go on each axis. Remember, the explanatory variable goes on the x-axis. Label and scale your axes. Plot the individual data values. Here's an example of a scatter plot. We place body weight along the x-axis and backpack weight on the y-axis. We plot the points. Here's another example of showing data. 13 students in a statistics class. Each member ran a 40-yard sprint and then did a long jump with a running start. A scatter plot of the relationship between sprint time in seconds and long jump distance in inches is shown. And here's a graph of the data. We look for patterns to interpret a scatter plot. We look for the overall pattern and departures from the pattern. You can describe the pattern of a scatter plot by the direction, the form, and the strength of the relationship. An important kind of departure is called an outlier, an individual value that falls outside of the overall pattern of the relationship. Here's an example of a scatter plot. This scatter plot is a moderately strong, positive, linear relationship between body weight and packing weight. It appears, then, that lighter students are carrying lighter backpacks. The strength is moderately strong, the direction would be positive, and the form is linear. There's one possible outlier, and that's the hiker with the body weight of 187 pounds seems to be carrying relatively less weight than the other group members. Two variables have a positive association when above average values of one tend to accompany above average values of the other, and when below average values also tend to occur together. Two variables have a negative association when above average values of one tend to accompany below average values of the other. Here we can see this is a moderately strong, negative, curved relationship between the percent of students in a state who take the SAT and the mean SAT math score. There are two distinct clusters of states and two possible outliers that fall outside of the overall pattern in this example. So here we're shown the strength, direction, and form. The strength is moderately strong, direction is negative, and the form is curved relationship. Here's another example of a scatter plot that would have a negative association. Again, we can see that there's one value that's a potential outlier over on the right, and that would be another example shown. Here's another example, low fat and low carb. And this would be for 9 different types of hamburgers at McDonald's. Here's an example of the 4 things as a reminder that we would use whenever we're asked to describe and interpret. State what we're looking for, write a plan of what you're going to do. In this case, the do part of our 4-step process would be using a scatter plot, and then we'd make conclusions based on the relationship and what we see in a scatter plot. Is it positive? Is it negative? Is it a strong or weak relationship that we see of the data? Linear or curved is also important to look at. Since we want to measure how strong a linear relationship is, we use what's called a correlation coefficient. R stands for the correlation coefficient. It measures the strength of a linear relationship between 2 quantitative variables. It is always a number between -1 and +1. If it's positive or greater than 0, we have a positive association. If R is less than 0, we indicate a negative association. If the values of R are near 0, indicates a very weak linear relationship. The strength of the linear relationship increases as R moves away from 0, either towards -1 or +1. The extreme values, R equals -1 and R equals +1, occur only in the case of a perfect linear relationship. Here are some examples to show what each of those would look like. We have the first one, a correlation of R equals 0. The next one is a negative 0.3 relationship. The next one indicates a positive 0.5 relationship. The one on the lower left is a negative 0.7 relationship. Notice the difference between a negative 0.3 and a negative 0.7. Getting closer again here to -1. On the middle bottom one, we have 0.9. Pretty close to forming a linear relationship. We can see the line forming, and then here we have negative relationship again, 0.99. Of negative 0.99 indicates in this case almost a straight line linear relationship, but not quite. So this is probably how close you would get in a correlation coefficient. You oftentimes have them somewhere in kind of the middle depending on what data you have. To calculate the value of R, we first look at the values for the individual of the first individual, that is x1 and y1, and the values for the second individual, x2, y2. We know that the standard deviations are given as s of x and s of y, and that the means are x bar and y bar. So the correlation between x and y looks kind of tricky, but it's actually a fairly simple formula to work with. We have our observation minus the mean divided by standard deviation for x. We have observation minus the mean divided by standard deviation for the y, which we essentially have already looked at in class. We take the sum, here's our sum sigma symbol for sum, add them together, the values, after we multiply these out, and then we either multiply by 1 over n minus 1, n standing for number of observations, or we divide by n minus 1. Remember that dividing by n minus 1 is the same as multiplying by 1 over n minus 1. Here's just another example to show what a problem might look like and what the scatter plot then would look like for the data, and some of the types of questions that we would be able to answer in order to talk about a correlation and a linear relationship in a problem. Here we have a scatter plot of sprint time and long jump distance data. In here we're showing a correlation coefficient of negative 0.75. So again, we're taking a look at what kind of relationship is it. It would be a negative correlation or a negative association. We can see that a negative 0.75 would mean that we have a fairly moderately strong negative relationship. It's asking here about what would happen if we would remove some of the points. Obviously, if we look at this and we remove some of the points on the relationship, we would have a different kind of scatter plot. And the closer, again, it gets to a straight line, the larger the correlation is between the variables. So here's some other examples of finding a correlation coefficient, and we'll do some practice in class as well about looking at graphs and figuring out correlation coefficients. And here's just a bunch of different ones to take a look at. And as you can see, it really depends on the data as to what our value of R is. Just remember that the closer it is to linear, the closer to 1 for positive or negative 1 association for negative. A few things about correlation. It makes no distinction between explanatory and response variables. It does not change when we change the units of measurement of x and y or both. The correlation R has no unit of measurement. It requires both variables be quantitative to use it. It does not describe curve relationships between variables, no matter how strong the relationship is. And correlation is not resistant. R is strongly affected by a few outlying observations. Correlation is not a complete summary of two-variable data. We will look at other ways to summarize two-variable data later in the class. Here's another example. The correlation was R equals 0.98, but it says Mrs. Stark's scores were about 5 points lower on average. We can see this in the scatter plot, which includes the line y equals x, which is shown right here in blue. So if both teachers gave an essay the same score, the score point for that essay would be on the y equals x line. All the points are below the line, which indicates that Mrs. Stark scored each essay lower than Mr. Smith did when you're comparing scores. It's important to be able to interpret the correlation and interpret the scatter plot when you're looking at data on a scatter plot. And that's it that we have for today for our lesson. In the next section, we'll start looking at the least squares regression line, making predictions. We'll look at what's called a residual and a residual plot, and finding the value of R squared in regression, and some more on correlation.